So yeah, today's going to be chapter 18, and then next week will be nothing but review for the final. So this is the last day of actual new topics, which is exciting. We're getting to the end. So don't forget when the final is. It's the Wednesday of finals week. We're getting there. But if we're ready, let's finish up the last bits of. It's not the classification slides. I just put some. I put some stuff at the end of the classification slides that doesn't have to do with chapter 17. And so let's start with that. So very, very, very quickly, I just want to talk about ethics and bias and things, because one day you might be in charge of data, right? As a data scientist, if that's what you become, you might be in charge of private data from people that like you have. Just by virtue of your position, you have this data accessible to you, and it's not something you should share with the whole world, right? So you have to make sure that you're handling the data ethically, and that when you do make little hypothesis tests and things, you got to make sure that you're collecting the data in a way that reduces bias. So let's talk about how to do the right thing, because that's what ethics is. If you've taken like a philosophy class, maybe you've had a section on ethics, or if you've taken CSI 1, maybe we teach about ethics. All that is the study of doing the right thing, almost. All right, what does it mean to do the right thing? So yeah, as you become a skilled data scientist, make sure to not do evil. So like I was trying to say, like if you're getting private data, most likely you're getting people's security, secure data. You're getting, maybe if you work at a bank, you have their social security numbers, you know how much money they make. If you work for like a social media company, like, I don't know, Facebook or Meta, whatever they're called these days, like you get all of their private messages, or if you work for TikTok, something like that. So like that's private data, you got to keep it private, right? So if you get access to private data and you're meant to do some sort of analysis for your boss or something, make sure to not like publicly post about it. That's very important. Don't do that. And a lot of the time, the private data should stay encrypted. Hopefully, you know what that means, just like password protected in a sense. Make sure that like it's on your work laptop. Make sure that it's behind two-factor authentication, like they forced upon us at school here. Make sure it's only on as many computers as you need it to be on, like download it only onto your work laptop, not onto like the cloud at your workplace, because that just makes it easier for like some bad person maybe to come in and steal it, or for it to get out from somebody else. So just those are the kinds of things you have to be thinking about when you're in charge of private data. There's also some rules depending on like what field you're like doing your data analysis in. So like if you're in the medical field, you've got HIPAA, which I don't know what that stands for, but like there's a lot of rules with how to deal with medical data, and like you'll have to learn that. Maybe you'll have to follow that. For example, at the school, like if somebody wants to use your student data, that's also protected. Like I'm not allowed to share your grades even with your parents. If your parents come and ask me what your grades are, I'm not allowed to say. So that's FERPA, that's protecting you there. So yeah, I don't even get to know your major, let alone talk to your parents. So just keep that in mind. Like one day you may have a lot of power, you may have access to private data, and you want to make sure that you're not doing anything nefarious. Okay, so that's important. And here is an old but relevant always tweet from COVID times, where somebody was trying to take, like they did the Proctorio thing probably, or something similar to Proctorio, where like you go on your own laptop and you try to take a test, and I'll just let you read that for a minute, because that's unfortunate. We need to talk about that. So that's really sad, right? So when you are doing machine learning, like when you're trying to, because that's what was happening, right? They were training their little software to see if somebody was cheating on their test, because like they don't have enough people to just like watch the video feed of a million people trying to take tests. So like they trained some AI probably on people taking tests, and this software couldn't recognize this person because they weren't white, and that's really unfortunate, right? So that goes to show that their training data, maybe the training data for the people trying to make this AI detect whether or not there was good lighting in the room, there probably wasn't a lot of like non-white people in that training data, and that's really unfortunate and sad. And so if you are like this goes to show like the kinds of things you have to worry about when you're trying to train a machine learning model. Like if you want this to work for everybody, you better be inclusive. Your training data better be inclusive of all people, and that avoids bias. So that's another thing to worry about. So one day you might be in charge of training a machine learning model, because that's the thing that data scientists do, and you'll have to be very careful to make sure that your model will work for anybody who wants to use it. All right. So make sure to get all the edge cases, corner cases, all the kinds of things that it could be used on in your training data, so that it knows, like, it can learn the correct thing. Yeah, so that's important. Another good example is the little Grok AI thing from the Twitter people. It was trained on probably some data that it shouldn't have been trained on, and so it says some horrible things like it said there in that screenshot. And so that just again goes to show that when you have training data and you're trying to make a machine learning model, you're trying to like make an AI or something, whatever you feed in is what you're going to get out. So if you feed in a bunch of people saying bad things, your AI is going to learn to say bad things, right? And so you're going to have to filter it sometimes, right? You want to filter it. So like ChatGPT, I assume it's been trained on the entirety of Wikipedia and things like that. It's also been trained on the entirety of probably Twitter and or X or whatever it's called now, and Reddit, and like there's plenty of places on the internet where people say mean things, right? And so you have to go in, and I'm sure that's what the OpenAI people did. You have to go in and like filter the bad stuff to make sure that your model doesn't learn how to be a bad person, right? So that's unfortunate. And so your model might be biased if you train it on biased data. All right, so that's unfortunate, and you need to watch out for that. And so you're also going to have to filter your training data, even though you want to give it stuff that's representative. You want to give it stuff that's nice as well, all right? Because you don't want it to learn how to, like, if it's an AI chatbot, you don't want it to learn to be like racist or say hate speech or anything like that. And so you do have to be careful. There's a very fine line between feeding a lot of data to your machine learning model so that it learns a lot of things, and also you feed it in too much data so that it learns to be biased in a certain way. Okay, so yeah, that's a bit more of a heavier topic, but I hope that makes sense. Like, use your skills for good and not evil is kind of the moral of the story, right? Any questions about any of that before we go to our last topic? So that is something to ponder and think about, and you might have to worry about that one day. All right. For my last trick, chapter 18 is the last chapter of our textbook. We're going to learn how to update our predictions with new data. So we've got a model, we've learned the way of the world, but we get some new data, which is nice. We learn more about the world. How does that update the things we want to make predictions of? So chapter 18 is the last little topic. Please read that. The way that we update our model with data, update our probability distributions with more data, it's called Bayes' rule. If you've heard of that, maybe you've taken a statistics class. It's called Bayes' rule. We're going to learn about it. But here is a made-up scenario, and it's going to motivate this topic. All right, so let's say we got this. You transfer to Berkeley, or you transfer to some four-year college, and you're sitting in the next data science class. And here's what goes on. So in that class that you're sitting in on, there are second-year students, so sophomores, and third-year students, juniors. There's only sophomores and juniors in the class. 60% are second years, 40% are third years. I guess you'll go in as a third year when you transfer, most likely. And so you know that that's the makeup of the class, right? And then 50% of the second-year students have declared their major. They say they know what they want to do. Like, they're like, I'm going to do data science. I'm going to do computer science. I'm going to do something. 50% of the second years have declared their major. And then 80% of the third years, you know that they have declared their major. So I guess by the time you're a junior, you know more about what you want to do. All right. And let's say, so that's the makeup of the class. And I pick one student in the class at random. The question is, who is more likely to be picked? A second-year student or a third-year student? With that data. Can you think about it? What are your thoughts? So I guess one thing we could do is we can turn this into a bi-clicker question. Might be the last one of the semester. Like if that's A and that's B, what do you think? Just can you reason about that in your mind? Because this is kind of motivating a new topic. It's kind of hard to think about this, but let me see what your gut tells you. If you would humor me and go to the bi-clicker page. Pick A or B. What do you think? You think it's a second year? I'm more likely to pick a second year student or a third year student. Or am I trying to trick you? You can kind of see it, right? Any thoughts? No thoughts? You see that's the makeup of the class. Now I pick one student at random. Are they more likely to be a second year student? That'll be option A, or third year student, option B. Some of this data is kind of useless to us, isn't it? There is an answer, right? But we're going to spice it up in a second. Whee. Nice. Okay. Nobody has responded, so what? Is there something wrong? What can I say? Are you just not feeling like responding today? Who's more likely to be picked? Or should I explain more? Like, what's confusing? Oh, thank you. Yeah. I'd like everybody to respond. If it's a 60-40 split, it's hopefully you can see what's happening, right? This data is kind of useless to us, right? Though it might be important later. So, thank you. Let's do this. It's for sure second years, right? They're 60% of the class. Are there any questions about that? That's really important that we understand that. This extra knowledge was useless to us, but we can change the question and make it more interesting, that's for sure. So it's if I just pick a student at random, they're more likely to be a second year student because there's more second year students in the class. But let's change the scenario. Let's say that the class looks similar. We got second year students and third year students, and still half of the second years have declared their major, 80% of the third years have declared their major. And now I pick a student at random, but I ask them, have you declared your major? See how that changes things? Because you know that there are more second years in the class, but you know that fewer of them have declared their major, right? If the student tells me when I ask them that they have declared their major, do you think that that might flip it over to like, okay, maybe they're more likely a third year now? Because even though there's fewer third years, more of them have declared their major. You see what's going on? So you kind of have to do this option in your head, these thoughts, right? What's more likely? You know that there's more second years, but fewer of those second years have declared their major. If you know that they've declared their major, what does that change, right? Whee. What does that change? So like here's kind of the makeup of the class, if I can try to do this accurately. You got 60% second years, 40% third years. This is what they look like. So here's the second years, here's the third years. And there's more second years than third years, but of the second years, only half of them have declared their major. Like exactly half of them have been like, I know my major. And just as many of them have been like, I don't know my major yet. And the third years, 80% of them know their major, 20% of them don't yet. So it looks more like that for them. Third years, 80% know their major, have declared one, 20% have not declared still. And we know that the students, somebody has declared their major. I pick a student at random, I ask them, have you declared your major? And they say, yes, I have. What are we more likely to be in now? Well, it's a question of like, are we here or are we here? And it's the one with the bigger area. Can you kind of see? They're kind of close. If I drew this accurately, this should have brought us over into the third years. It's ever so slightly more likely that they're going to be a third year student. And there's a way to solve for that. So that's really cool, right? So one way to figure out like how do we deal with this is to write some code and see what happens. Let's do that first. But there is another way, and we're going to learn the faster way. But here, let's do the slower way because we can always simulate this. All right. So here, we know. Let's make a column for all the students and what year they're in. So np.array. If I do, here's something cool that you can do. You can make if you start with a list and I say like second for second year, and you multiply it by something, second times 60, you get 60 things in that list, and then you can immediately turn it into an array. So here's an array of second years, and there's 60 of them. And I want to do the same with 40 third years. So I'll multiply this by, you don't have to understand how this is working, but like you can multiply lists in Python to get things. So here's like the class in terms of what year the students are. So I've got 60, let's pretend there's 100 students just for ease of percentages. There's 60 second year students, 40 third year students. That's accurate. Let's call that year. That's a column. And then let's say what their majors are. So remember that as these go in order, we want these to go in order. So for second years, if there's 60 second years, there are 30 undeclared, right? Half of them are undeclared. 30 undeclared second years and 30 declared second years. If there's 60 of them total, half and half. And then it's an 80-20 split for the third years, and we got to figure out what that is. And then for the third years, what's 80% of 40? Or I guess what's 20% if we want to do undeclared first. So if there's 40 of them, what's 20% of that? There's only 8 undeclared third years. And that means everybody else is declared. So 8 of them plus 32. So this is going to, we're going to put these in lockstep. So there's going to be 60 second years, then 40 for third years. Like here are the declared and undeclared second years, and then here's the undeclared and declared third years. And we're just going to line them up. So here, let's turn this into a table now. I'll call this major. So you can totally simulate this and count. That would totally work. So I'll call this students, make it a table with columns. Got year, major. And yeah, it's a big table, so I'm going to have to say students.show or something. So here's what I've done. I've just like made that many second years, that many third years, and I've put next to them the right proportion of undeclared and declared. So like this is the class. Here I've simulated the class. And we can start counting like, okay, how many, if I can split up on like how many of the second years are declared, how many third years are declared, and whichever one's more likely, whichever one has more people in it will be the more likely option, right? So yeah, this is the makeup of the class. You call on 10 students, they look like this maybe. So yeah, let's do, I think the easiest thing to do would be a pivot table. Students.pivot. Let's do the major on the X and the year on the Y. So here's the makeup. So you've got, for the second year students, 30 declared, 30 undeclared. For the third year students, 32 declared, 30, and then 8 undeclared. And so if we know that a student has declared their major, do you see, like you look at the declared column, there are ever so slightly more declared third years than second years. Isn't that crazy? So you can do the math, you can do the simulation. It's ever so slightly more likely for it to be a third year student. Yeah? Any questions about how you could simulate that? That took a lot of time though. There's a quicker way. Well, that's pretty neat in itself. Let's see. Yeah. So that's how we know it's more likely that it's a third year. But there is another way. It's called Bayes' rule. So here's how it works. Here is how to read what I'm trying to tell you. So what we want is we want to find the probability, right? The probability of second or third year. Again, just like we did for this question. It's like, what's the probability of being second year or third year? Same question, right? Was it second year or third year? But I also had some new knowledge. So there's a new way of doing this, all right? So we are trying to update our prediction of second year or third year with new information. We know, hey, did that student say that they declared their major? If so, that changes things, right? So what we want to do is solve for this kind of probability. And it's a new way of doing it, because we've solved for like this before. Like we've seen this kind of syntax before without this, like probability of it being a second year, for example. If you put this little line character, it's called a pipe character, you read it as given. So what we're trying to solve for is the probability that we have a second year student given that we know that they have declared their major. That's how you read that syntax. That's how you read the probability calculation that we're trying to do here. So I want to know, what is the probability that like we have a second year student given that they've declared their major? And we know that we can calculate that, right? The way that we did it here is like, all right, probability of a second year student knowing that they declared their major. It's like, all right, there's 30 declared second years out of 30 plus 32 declared people. So it's under 50%. Like that's what we're trying to solve for in a faster way, okay? So the probability that we have a second year student given that they have declared their major, okay? And yeah, let's talk about some of these things. So here is kind of like, it's this little split off of a thing. Well, this is what we know. Like this is these words in a table form. All right, so let's talk about this. This image is going to be important for us. So here is like the start of time, and here's the split of the class, right? There's 60% second year students, 40% third year students, and so you see how it splits in that direction. Can you see how that's working? 60% gets you to second year, 40% gets you to third year. Like this is the 100% of all the students, like, and this is how it splits off, kind of. All right. So this right here is the probability of student just being a second year student in the class. So this is this right here is the probability of being a second year student. Let me put it at the end of the arrow. So the probability of being a second year. And we call that the prior probability. It's just the probability before we know any extra information. That's the probability of there being a second year student. You just randomly pick somebody, okay? And so this is the prior probability of being a third year student. And then we have these things. If we split off, like if you know you have a second year student, you know that half of them are declared and half of them are undeclared. So it's a 50-50 split for second years, and it's an 80-20 split for third years. And what is this probability, this 0.5, in this kind of way of drawing it? This is the probability that a student is declared given that we know that they were a second year first. See how that's kind of the opposite of what we want? It's 50% to know, like, okay, 50% chance that a student has declared their major given that we know that they're a second year student. That was what we originally just knew. 50% of the second years have declared their major. Another way of writing that is saying the probability that we know a student has declared their major given that we knew first that they were a second year student. So in that order of gaining information. But that's backwards to what we want right now, okay? So, yeah, we want kind of the opposite of this, let's say, or same for third year. What we'd like to solve for, right, we want the other way around of this. What we'd like to solve for is we know that a student has declared their major, so we know that we're in one of these two spots, right? Let me draw a box around this. We know that we're either here, or maybe, yeah, let's do it like this. I know that I'm either here, right, or let's use green. I know that I'm either in this one, or this one, because we know that the student has declared their major, right? So I know I'm in one of these two. We know we're in one of these. In one of these options. Does that make sense? Like, all right, we know that a student has said that they've declared their major, so I know I'm in one of these options, but I'm not sure what's more likely. And I want to solve for, let's say, the probability that it's a second year student, given that they've declared their major. So I would really like to solve for this one. You could just as easily try to solve for this one. All right, it's like whichever one's more probable, whichever one's above 50 will be your answer. But that's what I want to get at. And does this diagram make enough sense to understand how to read it? It's like the split of all the students, right? I know that 60-40 split for second year, third year, and then once I've got second year students, I know that half of them have declared, half of them have not declared their major, 80-20 for declared and declared for the third year students. And I know if a student has declared their major that I'm guaranteed to not be in any of these. I know I'm in one of the declareds. I want to know what's the probability that I get a second year student given that I know that they've declared their major. So I kind of want to go backwards. Because these, like this 50 and this 80, that's the probability of being a declared given that you're a second year, probability that you're declared given you're a third year. Okay? So I want to turn it around. I want to turn it around on its side. And so I want to calculate what's called a posterior probability. So like prior means before, posterior means after, right? Post. So that's the probability of something after we've taken our new information into account. So I know I'm for sure not in this undeclared state, right? I'm in one of the declareds. Like which one's more likely is what I'm trying to calculate right now. Which one is more likely here? I'd like to figure that out, please. And so let's do that. This is going to be our formula. I'm going to show you how to do that. But let's see here. Right now, at the start, let's talk about this in general. So what I want to do, right, is solve for this. The probability that I got a second-year student on my hands, given I know that they've declared their major. And the way that you can solve for that, there's a nice little formula. It's called Bayes' formula. And you can solve for A given B if you know B given A. You can do it backwards after you multiply by some things. So you can flip it around. So like, see how this one is in terms of one that's flipped around? So you can flip it around if you do this math. So that means just following the rules. And so like this would be a formula that you put on your cheat sheet for the final exam. What you would do is like, all right, I want to know second year given declared. So that's equal to, just like pushing the symbols around, that's equal to the probability of knowing that a student has declared their major given that they're a second year times probability that they're a second year over the probability that they've declared their major. You just read it off the formula. All right, and let's try to solve for that. We've got, what's the probability that a student has declared their major given that they're a second year? That's this, right? 50%. So you can just read it off the table if you do it like this. 50% times the probability of just being a second year in general. That's the prior probability, 60%, 0.6. Over the probability that a student has declared their major. And that's going to be the harder one. All right, so what does it mean? What is the probability that a student has declared their major? So let's figure that out together. Okay. The way to know, like, what is the probability that a student just in general has declared their major at all? The way that this works is you can multiply probabilities. So what's the probability that a student is a second year student and they've declared their major? It's 0.6 times 0.5. That's how it's going to end up working. So it's going to be like, all right, if this was a 60% split, then this is going to be, if there's 60% of students right here in the second year column, so we know that half of that 60% is in declared and half of that 60% is in undeclared. So it's going to be a 30-30 split. You see how it's like multiplying 0.6 times 0.5? So that's 30% here, 30% here. Does that make sense? You can multiply that. It's like, all right, there's 60% of people over here. Half of that is declared, 0.5 times that of that is undeclared. So it's 30-30 over here. So 30% of everybody is a second year declared student. 30% of everyone in the class is a second year undeclared student. So it's like two things at once, and. And then same for third year. We know that 40% of the people in the third year column are declared, 40% of the third year column are either declared or undeclared, but they're third years. To get how many third year declared students, you just start with the 40% split and you take 80% of that 40 to know how many declared third years there were. And that's 0.4 times 0.8, which is 0.32. So that's 32% here. And then the remaining of the 40%, that's the 0.4 times 0.2. That's 8% undeclared. So there's 8% of everyone in the class is in third year and undeclared. It's like when you multiply, it's and. So third year and undeclared, third year and declared, it's 40 times 0.8. Yeah? Questions about how I solve for those percentages. You can just multiply them together. Because that'll give us what's the probability that anybody at all has declared themselves. It's either they were here or here, so it's just the 32 plus 30. So that's that. So what's the probability that anybody at all has declared their major? It's just the idea that, well, they were either here, 0.6 times 0.5, which we know is 30%. Plus, let me try to write this cleaner. 0.6 times 0.5, that was the declared second years, 30%. Plus 0.4, like this up. This is the other option, not 32. How did we get there? It's 0.4 times 0.8. Which is 32%. Cool. And so you just add them up. And that's the probability of just anybody at all being declared in some way. And yeah, that is That's how you can do it. Let's see here. Let's try to figure that out. Let's try to figure that out together. It's gonna become what we just discovered. It's gonna be 30, right? 30% over 30 plus over 32%. Because that's 0.6 times 0.5. 30% over 30% plus 32%. And so it comes back to exactly what we calculated before, but now we did it in a different way. All right, it is 48%. That's pretty neat. So it's just like the weight, the relative weight of, all right, I know that I'm declared somehow. Which one's like, for if it's a second year, what's the probability that I was a second year declared? Well, it's the 30 over just every option of being declared. Add them all up. So yeah, that's called Bayes' rule. You can calculate a posterior probability after I know that, okay, the student's a second year. Or I know that the student has declared their major. What's the probability that they're a second year now? And so you can turn things on the other end and solve for things. That's great. Any questions about that? Because this leads to some interesting thoughts. Maybe this was easy enough to read off and like do the simulation for, but sometimes it gets harder. So here's a weirder example. Again, Bayes' rule is that probability of A given that you know that B has happened is equal to the probability of B given that you know A has happened times the probability of A over the probability of B. All right. So here is the standard way of teaching this. The way that people usually teach this is it's in terms of like a test for a disease. So here's an example test for a disease. So let's say that you've got a very rare disease. It's very unlikely for a person just randomly picked in the population to have this disease. So it's like 0.4% likely that you'd ever have this disease in general. And it's very, very likely, 99.6% likely that you'll never have this disease. But if you have the disease, you've got a good test for it. You know that it's a 99% positive test rate. If you have the disease, it will not usually be wrong. Sometimes if you have the disease, 1% of the time it will test negative and it would lie to you and tell you that you didn't really have it. But usually 99% of the time, if you have that unlikely disease, 99% of the time it will tell you that it was a positive result. If you're one of the people that didn't have the disease, usually it will tell you that you don't have it, the test. 99.5% of the time, it'll tell you that you got a negative test result, which is correct for you not having the disease, but also sometimes it will lie. Tests are not always accurate. So 0.5% of the time, if you actually didn't have the disease, it will tell you falsely that you really did have it. And so then you have to get more tests to verify that it wasn't really there. And so usually it's accurate, though. If you didn't have a disease, most of the time it's telling you you didn't have it. If you do have the disease, most of the time it's telling you that you did have it. All right? So we want to ask the question of how likely is it that we have the disease if we got a positive test result? All right. So say that you got some random person in the population, you test them with this supposedly very accurate test, and you know that their test is positive. Would you tell them that they actually had the disease, though? That's the question now. So try to do this. So you know that their test was positive, and you want to say, hey, do you have a disease or not? Do you have this disease or do you not have this disease? Maybe it's COVID or something. So you want to solve for, hey, the probability of a person having a disease given that you know that they tested positive, right? And so you know a few things. You know the probability. This is like the probability that they had the disease. This is the probability that they did not have the disease. Probability of like no disease. Let's say ND for that. And then these guys, they're the wrong way. This is the disease given that we're trying to solve for a disease given that we know that they tested positive. This is the probability that we have a positive test result given that they had the disease. So it's backwards. All right. So you want to flip that. You want to solve for the flip of that. And so try to set it up. Try to solve for this, given this knowledge. I'll give you a couple minute head start. You don't have to write it down anywhere, but try it. Try to use that formula. You want to solve for what's the probability that you actually have the disease, given that it was a positive test result. And we're going to notice something very fun. That's the reason I love it. It's called Bayes' rule. You kind of see how we did it. If you want probably a bunch of things at once, something and something else, you have to multiply. So the probability that you had the disease and you tested positive was 0.004 times 0.99. To do an and, you multiply the chain together. And so yeah, if we know that they didn't have, or if we know that they tested positive, we know that we're either here or here, right? I gotta figure out which one is more likely. Which one is more likely? It might be surprising. Nice. Perfect. All right, let me solve it for you. Was it what you were expecting? Let's see. So what we want is probability of disease given that they tested positive. So I'll write that like this. So P, I'll just say D for disease given that we know that they tested positive for that disease. That's equal to these guys. So the probability of the flip side, probability of a positive test given that they had the disease, times, we try to follow that's like the second thing again, probability of just the second thing, probability of that they had the disease in general, over the probability of this first thing, which is just having a positive test at all. Boop. So that is what we want to solve for, to know like what's the probability that they actually have the disease given that they tested positive. So the way that we solve for this is we pick out the pieces we know we have. So the probability that we have a positive test result given that somebody had a disease is this. Yeah, it's 0.99, 99% chance that they get a positive test result if they had the disease. So that it was correct, not telling them that they didn't have it when they did. So we have that. Probability of having the disease in general, that's your prior probability. It's this thing, 0.004. Very, very unlikely for you to have this disease. So that's the probability of you having it at all. And then I accidentally deleted a parenthesis. Now the last thing is, what's the probability that you actually had a positive result? It is either, it's the addition of like how we got here and how we got here, right? So what's the probability that we're in this situation? Well, it's going to be disease and positive. So 0.004 times 0.99 times 0.99, which is kind of the first half of this, if you think about it. It's your numerator. First half of the bottom is your numerator all over again. And then how do we get to here? What's the other option for having a positive test? It's 0.996, and it was wrong because we didn't actually have it. 996 times 0.005. All right, so now the question is, what is that? Let's try to figure it out. So 0.004 times 0.99. Honestly, to solve the question, like what's more likely, just do like this times this and do this times this and like figure out the probabilities of each. You just like see which one's bigger is kind of the answer. But we can also calculate the full probability. So like, all right, what's the probability that you had a positive test result and you had the disease? 0.004 times 0.99, it was right. So 0.396% chance of you having the disease in a positive test. And then what's the probability that you had a positive test but you didn't have the disease? Well, it's 0.996 times 0.005, right? Which is surprisingly a little bit bigger of a percentage. So it was more likely that you actually didn't have the disease. It was just a false positive. Crazy. So the full probability is that 0.99 times 0.004, so this guy, over that, again, plus 0.004 times 0.99 plus 0.996 times 0.005, which is this. So it's the probability of you having the disease given that you got a positive test result. It is 1.3%. So it's like 98% more likely that even though you got a positive test result that you didn't have the disease. Because that would be the opposite. Isn't that crazy? That's crazy. Oh wait, I think I might have done. Oh, sorry, it was supposed to be a division. My bad. It's much closer. It's a 44% chance. Sorry, 44% chance that you actually had the disease at all. So it's less likely that you had the disease, more likely that you really didn't have it. That's crazy. So that is a little paradoxical. Like, this test was supposed to be really good, 99% chance. It told you the right thing if you were positive. So very unlikely it gave you a false positive when you didn't have the disease. But actually, because it was so unlikely, this 0.996 here was carrying a lot of weight. You see that? Because it was so unlikely to have the disease at all, it was more likely to just have a false positive, even though the test was decently accurate. Crazy. Any questions about that? Does that make sense? That's funny. Seems wrong, but that's how you solve for that. That's how you know. So, let's see here. What do I want to do? So, you could also simulate this. Let me just copy and paste it. I think that's easier. Boop. Or do I want to type it in? Let's see. No, that seems like way too much. I want to be here. Let me show you something. We could also do the simulation. Again, it would work. You just have to be very careful about how many people are there, how many people you simulate. So here's how you could do the simulation. Here is how you could build it up. If you have, what are our percentages? We got like thousandths of a percent. So you have to be very careful about how many people we're pretending to have here. So like for this, it was like 0.6 and 0.5. So we could have had like 100 students, that was fine. But for this one, we have like 0.004. So we'd have fractions of people if we started with 100 people. So let's just like, to get around all that, because you're going to be multiplying things and having like really, really small values. This is like 100,000ths of something. So let's pretend we have 100,000 people. All right. And yeah, here's our probability of having disease at all, 0.004. Here is the number of people, n underscore d, number of people who had the disease at all, then was prior probability of having the disease times, let's say we've got 100,000 people in our population. That will get rid of any decimals and like turn it into an integer. Number of people who didn't have the disease is, pretending we have 100,000 people, that minus the number of people who did. Number of people who had a positive result given that they had the disease is, well, the number of people who had the disease times 0.99, integer version of that, because it'll do float stuff. Number of people who had the negative version of that negative result given that they had the disease, well, it's the number of people that had the disease at all, minus the people who had the positive result. That's the negative people. And then you just keep on playing this game. I hope you can kind of see it. It's like number of positive people who got a positive result given that they did not have the disease. Well, it's the number of people who didn't have the disease times that rate of getting that false positive, that 0.005. So there's that. And the negative is the flip of that. It's like everybody else who didn't have the disease is in that camp. And then you can turn this into a very, very long set of arrays, right? People who had disease and no disease, that many people. And then positive disease, negative disease, positive result, no disease, negative result, no disease. You just bring them all together like we were doing. And like, yeah, you have a really, really long table. And you can do a pivot on that like we were doing. t.pivot, test result. And it was true condition. Like what do they actually have? Do they actually have the disease or not the disease? And then it'll take a while because it's a very long table. It's like, all right, the people, if you're looking at people who did have the disease, this many negative, this many positive. People who didn't have the disease, this many negative, this many positive. There's a lot of people who didn't have the disease, right, and had a negative result. But all right, if you had a positive result, you're in one of these camps. It was more likely, just because it was such an unlikely disease, it was more likely for you to not have it at all. And it was a false positive. Isn't that crazy? So that's why we learn about this, because it's a little paradoxical. That's why we want the numbers. Okay. Any questions about that? So you can simulate it. You could also solve for it. I just want you to get good at understanding these kinds of images, right? And do this kind of calculation. Very easy thing that I could be asking you on the final, right? All right. Yeah. But usually, let's say you're a doctor, or like you're making this this data science software for somebody in the medical field. It's very likely that somebody came to get this test, right? They thought they had the disease, right? If somebody's getting a test for the disease, there's probably a reason that they're getting that test. Maybe their doctor saw something, they want to like follow up. It kind of changes things. It's called a subjective prior. Like somebody coming into the doctor's office asking for a test, they're not actually a random person in the population, because this what we've solved for is something true for somebody randomly picked out of the population. Somebody coming to the doctor because they think they have a problem, they are not a random person anymore. Does that make sense? They are not just a random person off the street. It is not a random chance that we picked them. So the doctor can be a little bit more subjective with the way that they're calculating things. So here was our original way of calculating this. We really like to figure out, well, is it more likely that we got a positive test result, or we know that the test was positive for this person, and so we're either here or here. What's more likely? Well, let's say that the doctor has an opinion now. Okay, you coming into this doctor's office means that maybe there's a bit more of a likelihood that you really did have that disease. So it's not 0.004 anymore, but it's like maybe it's 5%. Let's say that's the doctor's subjective opinion. That's a subjective prior now, all right? Doing that was going to swing everything, all right? So that changes. It's 0.5 instead of 0.004 all over the place, yeah? That's going to change a lot. And so you might have to switch things up. So like this becomes 0.05. This becomes 0.05, right? Boop, just like that. And then this becomes not 0.996, but the rest is now just 95%. 0.95, and that changes a lot. And so if you solve for that, originally this was like 44% up here. For the original one, it's like less likely for this to be true. It's about 0.44. Originally this was, right, originally it was, using green again, 0.44. But if you change this around and you solve for it, I did this ahead of time, it's going to be much more likely. This is going to be like a 91% chance now that they actually had the disease given that it tested positive. So like it wasn't just a random person walking into the doctor's office. And so that might change your prior probabilities a little bit. And that might flip things in favor of something else. Okay? That might flip your results in favor of something else. That's crazy. That's pretty cool to think about. And that, I think that's the last thing that I wanted to say. So sometimes when you know this data, maybe the prior probability isn't what it should be, because like the kinds of people you see are not randomly selected from the population. Isn't that fun? So you can also simulate that, of course. You'd be like, all right, again, the prior probability of having the disease this time is 0.05. I think everything else stays the same. 99%, 0.005 for was it a good test or not. So like make that table again. If you pivot, now you can see with that new idea of how likely it was to have the test. Now, okay, if it's a positive result, you're decently more likely to have the disease versus not have the disease. Cool. And yeah, so somebody coming into the doctor's office might be a little bit more likely to have it than just some random person you pick off the street. That is the moral of that story. But yeah, this chapter just focuses on this idea called Bayes' rule, where you have, like, you want to update your thoughts. Like, we know we've got some new data, we've been given something. How does that change? We've been given some data on B. How does that change our probability of A? And so you can solve for it in this kind of way if you have a table that looks like this, a chart that looks like this. Okay? And I think that is what I wanted to say about this chapter. It's not the world's longest chapter. It's a nice, easy one to end off on. Any questions about that? So I think that's where I want to stop. We're just going to do a bunch of review next week. So just the 2 lectures next week will be reviews for the final. And remember when the final is, of course. Check out that final info page. The last thing I want to do is talk about your last assignment. So because we had a lot of Monday holidays this semester, and so like we have like 1 or 2 fewer lectures than you would if we had this class in the fall. And so I need to release, there's 2 more assignments that have not yet been released. There's homework, or they've been released, but they've not been like set due dates for. And we've got homework 12 and lab 10. And if we look on the schedule, we already have something due next Friday, because that's our project 3. And I think I'm good to assign something due a week from now, Wednesday. But I don't want to like double up the due dates. That would be evil for you guys. So usually there's enough time for it in the fall semester, but there's not enough time for everything to assign everything and have it be due on separate days for the spring semester. So lab 10 is the stuff on this chapter. It's the new stuff. Project 3 is still about chapter 17. Homework 12 is also about chapter 17, about doing classification stuff. So it's just like another review of that. So you're already getting that information in Project 3. So here's what I'll do, all right? My gift to you is I'm going to assign Lab 10. That one's more important because that's on the new stuff that we just covered today. I'll assign Lab 10 to be due next week, the 13th. The 13th. And then here's what I'll do for homework 12. We will talk about it. So lab 10, this one will actually be due the 13th normally. Homework 12, every assignment is due next week. Like there's nothing due during finals week. So what I'll do for homework 12 is I'm going to make it extra credit. All right, if you want to do it, you'll get, I'm going to make it be 1% extra credit on top of your final grade. All right, if you do it. So that's what I'll do. And I'll make it so that you don't have to do it if you don't want to. So everything's going to be due on next Friday. So like I'm going to set the due date for Friday just so that it's in there. But again, for homework 12, this one will be extra credit. All right. So you don't have to do it if you don't want to. It'll be extra credit if you do it. And so let me in Canvas, I'm going to need to set and make sure that like that changes. So because I drop a few of your like lowest scoring assignments. And so for homework 12, here's my rule. Drop the lowest. I'm dropping the lowest 2 right now. Let me just drop the lowest 3 then. Cool. There. So now if you don't do it, it's like it never happened. But if you do it, I will see that and I will give you some extra credit. All right? Does that sound good? And so I think that is what I wanted to say. So yeah, you do not have to do homework 12 if you don't want to. It is going to cover the same kinds of things that Project 3 is covering, more or less. But it will only help you for the final, of course. And I'll definitely be asking you about classification stuff. So there's that. Lab 10 has a real due date, and that will be the last real assignment before Friday, which is the project as well. So cool. So yeah, homework 12, extra credit, 1% extra credit if you do it. But everything will be due on Friday, next week, Friday. That's when every assignment will be due. And that's when I accept late submissions up to as well. Okay, so I'll talk more about that next week, but does that make sense for the last few assignments? What you need to do? All right. So yeah, I think that's all that I wanted to say today. Everything has been assigned at this point. That's great.